In this video, we're going to learn all about logarithmic functions, exactly what they are, a lot of their properties, how to deal with them, and all sorts of great things about them. Now, logarithms tend to be something that students seem to really struggle with, and I truly believe that's just due to the notation. It is a tricky concept to get the hang of, and the notation is outright horrible. But if you can handle exponents, you can handle logarithms, because logarithms are exponents. They just don't always make that very clear when they're teaching it. So that's the important thing we need to learn, is that logarithms are exponents. Let's start with our definition. If x and b are real numbers, with b not equal to 1, then y equals log base b of x is called the logarithmic function with base b. And now the important part of the definition is how we actually calculate these things. What you need to know is that y equals log base b of x means the exact same thing as b to the y power equals x. It's the same exact thing. So this b that's written underneath the log, that's your base. Notice that matches the base of the exponential function. I have the opposite side is y, that's called the logarithm, but I like to call it the exponent because when you rewrite it this way, that side is the exponent. And then inside the logarithm, we have what's called the argument. But a lot of times I like to think of that as the answer, which sounds a little silly, but it's so when I rewrite it, it says b to the exponent is the answer, which makes sense to me. So always think about rearranging this logarithm so it's an exponential form. It's very good to get used to converting back and forth between exponential and logarithmic form, because sometimes it's easier to solve a problem with one and sometimes it's easier with the other. So we're going to just start with some examples where we rewrite logarithms into exponential form and then rewrite exponential functions into logarithmic form. So first, write in exponential form. My first one is going to be log base 3 of 9 equals 2. And I want to write this as an exponential rather than a logarithm. So remember that these things are equivalent. I need to have my base, which is 3. The base of the logarithm is the same thing as the base of the exponential. But then the exponent is the opposite side of the equation. So I get 3 to the second power equals the stuff in the parentheses there. 3 squared equals 9, which is a statement we know is true. This is just a different way of writing the same exact statement. Let's try writing another one in exponential form. I have log base 10 of 1 over 1,000 is equal to negative 3. To write this in exponential form, I would need to write my base to the opposite side of the equation is equal to the stuff in the parentheses. So I get 10 to the negative third power is 1/1000, which is true. Remember, a negative exponent would flip this underneath the fraction, so it'd be 1 over 10 to the third, and that would get you the 1 over 1,000. All right, so that's how we switch from a logarithm to an exponential. It's base to the other side of the equation equals the stuff that's inside the logarithm. Now let's go the other way around. We are going to write in logarithmic form. And my first one is 2 to the 5th is equal to 32. And I want to write this as a logarithm. So the easiest part is figuring out what the base of the logarithm is, because the base of the logarithm is also the base of the exponential. So I know I'm going to have a log base 2. We just have to figure out what goes in which spot. And this is where it's helpful to remember that logarithms are exponents. So on this side, I'm going to have a logarithm. On the other side, I'm going to have the exponent because they're the same exact thing. So I have the exponent goes on the other side of the equation, which means this 32 has to go in the parentheses. 2 to the 5th is equal to 32 is the same thing as log base 2 of 32 equals 5. Try another one. We have 1/8 to the negative 2 power equals 64. So again, you find your base by looking at what has the exponent. So I have a log with a base of 1/8. Logarithms are equal to exponents, so I have to put the exponent on the other side. And that means the 64 is the input for the logarithm. Log base 1/8 of 64 equals negative 2 is the same thing as 1/8 to the negative 2 equals 64. All right. Now we're going to learn a quick property of exponents that we're going to use to evaluate some logarithms. If b, x, and y are real, with b positive and b is not 1, then b to the x equals b to the y implies that x is equal to y. So this is saying if you have two exponentials and the bases are identical and they're set equal to each other like this, well then the exponents have to be equal as well. We're going to use that to evaluate a logarithm. Log base 5 of 125. And right now you're thinking, that looks absolutely nothing like this property here. And you're right, it doesn't right now. But remember that logarithms are the same thing as exponents. So I'm going to rewrite this so it involves exponents, and then I can use this property. So I'm just going to go ahead and say that this log base 5 of 125 is equal to something, and I'm just going to call that something y. Now if I rewrite this in exponential form, I get 5 to the y power is equal to 125. Can I write 125 as 5 to some power? I can. 125 is the same thing as 5 to the third. So I have 5 to the y equals 5 to the third, and using my property up above, this means that y is equal to 3. So that means that log base 5 of 125 is equal to 3, and that is correct. So there's all sorts of different logarithms, all the different bases that we can have. But most of the time we work with just two types of logarithms, the common log and the natural log. So the logarithmic function of base 10 is called the common log. or common logarithmic function. And it is denoted by y equals log of x. And notice we don't even write the base 10 down there because this is one of the most commonly used logarithms, so we don't even bother writing the base down. We just have log with no base written. That implies that it's log base 10. We also have our logarithmic function of base e. And that is the natural logarithmic function, or the natural log function. And it is denoted by y equals ln of x. So that one's completely different notation. In case you're wondering why it's ln and not nl, that's actually because in French, I don't speak French, but in French, the words for natural logarithm are written in the order logarithm natural, and this notation comes from the French for natural logarithm. So that's why the order seems backwards in the English language, because it's based on a different language. So if you look at your calculators, you should have a button for the common log and for the natural log. So a lot of the times, even if we come across other logarithms, we're going to try to rewrite them in terms of these guys because we have buttons on our calculators to evaluate them. By the end of this video, you'll learn how to change any logarithm to one of these guys. I would say if you have to try to develop a preference between the two, I would go for the natural log. If you're going to keep going on in mathematics, this natural log ends up being the most important logarithm of them all. So I would focus mostly on working with the natural log, but I know some other sciences prefer common log. So it's good to know both of them. Let's work with this common log and this natural log so we get used to them a little bit. We are going to calculate the common log of 10 million and the natural log of e to the fifth. Well, I'm going to start with that common log. And of course, you could honestly just type it into your calculators and you would be able to get the right answer. But these ones we can calculate without a calculator. So I know log of 10 million is going to be equal to something, so I'm going to call it y. And now I can rewrite this in exponential form. 10 to the y equals 10 million. And now I just have to figure out, can I rewrite this right side so it's 10 to some power? And I can. Each time you multiply by 10, you end up adding another 0 to the end of this. So I know that 10 to the 1, 2, 3, 4, 5, 6, 7th power will get me 10 million because that's how many zeros I have. So 10 to the y equals 10 to the 7th, and that tells me y equals 7. So log of 10 million is 7. And you can go ahead and type it into your calculator if you want using your common log button, and you'll get the answer of 7 as well. Now let's work with natural log of e to the 5th. So natural log of e to the 5th, I know is going to be equal to something, so I'm just going to call it y. And now I'm going to write an exponential form. The base of the natural log is e. So I have e to the y power equals the stuff in the parentheses. E to the y equals e to the 5th. And then I can already use that property to get y equals 5. So natural log of e to the 5th is 5. And again, you can type that in your calculator and see that it does work out just like that. So that's how you can calculate common logs and natural logs when the values are nice enough. But if they're not nice, you're going to have to use the calculator to get the exact answer. So for example, if I try to find log of 229 or the natural log of pi, I'm not going to be able to do these using the same method that we just did. The reason for that is because if I write log of 229 equals y, 10 to the y equals 229, I get stuck at this point because I cannot write 229 as 10 to a power. I do happen to know that 10 squared is 100 and 10 to the third is 1,000. So this y value is going to be something between 2 and 3, but that's about as good as I can get without a calculator. So since I can't do this, we would just have to type into our calculators log of 229. And we know it should be a number between 2 and 3. And actually, to 4 decimal places, I get 2.3598. Now, similarly for this guy, natural log of pi. If I write that equals y and rewrite it as an exponential, I get e to the y equals pi. And then you're stuck. And you're stuck because you have no idea how to write pi as a power of e. But what we do know, e is 2.718-ish, pi is 3.14-ish. So this y has to be between 1 and 2 because e to the first power is smaller than pi and e to the second power is bigger than pi. But that's as good as I can get, is between 1 and 2. But if I type into my calculator natural log of pi, to 4 decimal places, I get 1.1447. So sometimes you are going to have to use your calculator because these are very difficult to calculate by hand. About the best you can do most of the time is just estimate, oh, it's between these two integers, like I was doing before I told you to type it into your calculator. So let's learn a few properties of logarithms, and we're going to have a few more later in the video. So here's some of our properties. Log of any base of 1 is equal to 0. And the reason for that is because if I write this in exponential form, I get b to the 0 is equal to 1. And we already know that's true from our exponent rules. So log base b of 1 equals 0 just means the same thing as b to the 0 equals 1. Log base b of b is equal to 1, no matter what the base is. This is, again, if you write it in exponential form, because b to the first power is equal to b. Another property, log base b of b to the x power is equal to x. And this is, if I write it in exponential form, b to the x power equals b to the x power, which is very, very true. And my last property for now is b to the log base bx power is also equal to x. This one's a little harder to see. If I rewrite this in logarithmic form, I would have a log base b of the other side of the equation is equal to the exponent. And that is a true statement. So what I want to point out with these 4 properties here is look at properties 3 and 4 in particular. This is saying if I plug an exponential function of the same base into a logarithmic function, I get x. And when I plug a logarithmic function into an exponential function, I get x. That should sound familiar from something just a couple videos ago. Logarithms and exponential functions are inverses of each other. When I plug one of them into the other, I'm getting x. That's the definition of an inverse function. It's just very important to notice that these have the same base. They need to have the same base to be inverses of each other. Let's do some examples using these few properties. We have more properties to come later in the video. The example, log base pi of 1. Well, using one of our properties, property 1, we know log of any base of 1 is equal to 0, because pi to the 0 will be 1. Okay, how about natural log of e? Well, what's the base of a natural log? The base of a natural log is e. And our second property says log base b of b is 1. So this is log base e of e. That's also 1, because e to the first power equals e. What about log base 9 of 9 to the square root of 2? That looks pretty terrifying, but this is property 3. I have a log with a base of 9, and I have an exponential with a base of 9. So they undo each other because they're inverses, and the result is just that square root of 2. Now, when using that last property, I have e to the natural log of 6. So my exponential has base e, my logarithm has base e. So they're inverses of each other, so this composition will just give me the input of 6 as the result. That was that fourth property. So now we need to look at what does the graph of a logarithm look like? Well, kind of like exponentials, we have two graphs for logarithms, depending on what the base is. And just like exponentials as well, there's a special point. For exponentials, the special point was at 0, 1. For logarithms, it's at 1, 0. So your logarithmic functions can look like one of two graphs. I have one graph that has this vertical asymptote here, and it just goes up like this. This is log base b of x when b is bigger than 1. So it goes up forever, but it goes up kind of slowly. And it goes down forever here, matching the vertical asymptote of our y-axis. My other logarithmic graph looks very similar, just reflected. This is log base b of x, where b is between 0 and 1. And if you tilt your head to the side, this kind of looks like our exponential graph. And there's a reason for that, and it's because they're inverses of each other. So if you have the graph of one function and you need the graph of the inverse, you actually get to reflect it across this diagonal line, y equals x. And that will get you the graph of the inverse. To reflect it across that diagonal line, it's the same thing as flipping it over the y-axis and then flipping it over the x-axis. So, this graph of log base b of x, we have a domain of 0 to infinity, and we don't include 0 because we just get close to it with our asymptote. Our range is always negative infinity to positive infinity. We have a vertical asymptote at x equals 0, and we have that very special point of 1, 0 that occurs regardless of which base we have. So all of your logarithmic functions look like this when they're graphed. So now that we know what logarithms look like, we can graph more complicated functions involving logarithms by using our transformations of graphs, like what we've done before. So an example, let's graph the function g of x equals log base 3 of x minus 4 plus 1. And then we're going to write the domain in interval notation. And identify the vertical asymptote. All right, so I know I'm going to be shifting my graph around. I will take my original log base 3 of x graph, and it's going to be shifted to the right 4 and up 1. So let me get our basic graph down first. We know it has a point at 1, 0, and I know it's going up in this manner. But let me get a couple points just to be more accurate. I know that log base 3 of 3 is going to get me 1. So I know I have my function going up like this, and I know it has this asymptote here. So that's pretty close to log base 3 of x. And now I'm going to take this graph and shift it using my transformations. I know I need to go to the right 4 and up 1. So let me take the couple of points that I have and move them. So this point, I'm going to move to the right 4 and up 1. This point moves to the right 4 spots and moves up 1. So that's up here. Now the tricky part is my asymptote. Moving my asymptote up doesn't change it at all, but moving to the right does. So moving to the right 4, my asymptote right now is at my y-axis. If I move it to the right 4 spots, 1, 2, 3, 4, I would have an asymptote here. So let me connect that and connect it using my new asymptote, and I get the same exact graph. It's just moved to the right and shifted up a little bit. This is my graph of g that we needed. Now, what is the domain? I have to look at my x values. I'm not touching x equals 4, but I start right near there and keep going to the right forever. So my domain is 4 to infinity, and my vertical asymptote is now at x equals 4 because it's shifted to the right 4 spots from where it was to begin with. So one thing that's very, very important, you notice my domain changed when I had a different input from my logarithm. The input of your logarithm has to always be positive. It's only defined for positive values. So your input of a log must be positive. We're going to use that fact to find the domain of some various logarithmic functions. So write the domain in interval notation. And my first one is log base 4 of 1 minus 3x. That's my function. What's the domain? Well, remember, we can only have positive inputs for our logarithm. So to find the domain, you take the input, which is 1 minus 3x, and you have to set it greater than 0, because that makes it positive. Now I just have an inequality to solve. I personally would solve this by adding the 3x to the other side, and then I will divide by 3. When I divide by 3, I get 1/3 is greater than x. That's the same thing as x being less than 1/3. So my domain goes to all the way to negative infinity and up to positive 1/3, and I don't include that in my domain. So x is less than 1/3, so in interval notation, negative infinity to 1/3. Let's do a slightly harder one for part B. Part B. We have the natural log of 64 minus x squared. So we know we want the input, 64 minus x squared, to be bigger than 0. And the way I like to solve these is first I pretend it's equal to 0, and then I test things on a number line. So I'm going to just treat this like it's equal to 0 for now, and I'm going to start by factoring. 64 minus x squared is the same thing as an 8 minus x times an 8 plus x. I want this to be bigger than 0. What are the values that would make this equal to 0? Well, x equals 8 or x equals negative 8 would make this equal to 0. So I'm going to put those values on a number line and see how those values chop my number line into 3 pieces. I'm going to test the value in each of these 3 pieces to see if my inequality is true or not. So over here I'm going to use negative 9. In the middle I'll use 0. And over here I'll use 9. It doesn't matter what numbers you use as long as you're choosing one from each piece. So what happens if I plug in negative 9? 8 minus negative 9 would be positive 17. And 8 plus negative 9 would be a negative 1. So I have positive times negative, which is negative. So it's not going to be greater than 0. This is negative. So it's not true over there. What happens when I plug in 0? I'd have 8 times 8, which is 64. 64 is positive. So I know this part is okay. When I plug in a 9 to check, the 8 plus 9 is positive. 8 minus 9 is negative. Negative times positive is negative. And I wanted stuff to be positive. So my domain ends up being just this chunk of the number line where I got a positive result. Negative 8 to positive 8 is my domain. All right, well now as promised, we are going to learn a few more properties of logarithms. And I'm going to start with number 5 because we already did properties 1 through 4 earlier. We have a product property that says a log base b of x times y is equal to log base b of x plus log base b of y. This is very similar to that exponent property that said when we multiply things with the same base, you add the exponents. This is the very same idea. Similarly, if I have log base b of x divided by y, I can split that up with subtraction. So log base b of x minus log base b of y. And then the last property, log base b of x to a power. The power can come in front and multiply onto the logarithm. These 3 properties tend to come in handy when you're solving problems involving logarithms. And they come back again in calculus once you have to do more things with logarithms there. So these are good properties to learn. we're going to do an example, couple examples, writing a whole bunch of logarithms using these properties. So first, we're going to do some examples where we write as a sum or difference of logarithms. So we're going to have a logarithm with a bunch of complicated stuff in it, and we're going to use our properties to split it into lots of logarithms, but with easy stuff in them. So our first one, natural log of a to the 4th times b divided by c to the 9th. So that's a lot of complicated stuff inside of my logarithm. The first thing I happen to notice is that I have a gigantic fraction in this logarithm. So I can use that property involving division to rewrite this as natural log of the top minus natural log of the bottom. So far, so good. Now when I look at this first logarithm here, I have two things being multiplied together. So I can split that up using addition. So I have natural log of a to the 4th plus natural log of b, and I still have my minus natural log of c to the 9th. Now this natural log of b here is as easy as it gets. I can't write it any other way. That's as simplified as I can get it. But this natural log of a to the 4th and natural log of c to the 9th, I can do more because I have a power on those two guys. That last property says the power can come down in the front and multiply. So when I do that, I'm going to have the 4 comes in front, and I get 4 natural log of a. I still have my natural log of b. And then for this natural log of c to the 9th, the 9 gets to come down in front, and I get minus 9 natural log of c. And so I took this natural log of something very complicated and wrote it as a sum or difference of logarithms with easier inputs. Let's do another one like that. I have log base 5 of the cube root of 25 over a squared plus b squared. Well, that looks terrible, doesn't it? Well, the first thing I notice is I have a really nasty cube root. We know cube roots are the same thing as a 1/3 power. So I'm going to first write this as a 1/3 power. So I have 25 over a squared plus b squared, all to the 1/3. And now I can bring that 1/3 power in the front using that very last property of logarithms. 1/3 times log base 5 of 25 over a squared plus b squared. So now inside my logarithm, I have a quotient. So I can split it up using subtraction. So I have my 1/3 on the outside, and I get log base 5 of the top minus log base 5 of the bottom. And I need one more parenthesis. All right, let's see if we can simplify this even more. Do we know what log base 5 of 25 is? We do. It might be a little hard to see right away, but remember, this is saying 5 to what power gives me 25? And that's 2. 5 squared equals 25. So I can write that log base 5 of 25 as just 2. because 5 squared is 25. And now on this guy, I can bring that 2 down in the front to get 2 log base 5 of a squared plus b. And that's really all that I can do. Inside of this logarithm, I have addition, and I don't have a rule that allows me to simplify that. I only have a rule that allows me to simplify when I have multiplication, powers, or division in there, not a plus. It's about all I can do to finish it up if I wanted is distribute that 1/3 to get 2/3 minus 2/3 log base 5 of a squared plus b. And that's about as simplified as I can get it. All right, so that's how you take a complicated log and split it into simpler logs. Now we're going to do the opposite. We're going to have simpler logs, and we're going to smush it all together into one logarithm. So write as a single logarithm. And we have log base 3 of 54 plus log base 3 of 10 minus log base 3 of 20. And I'm just going to work this from left to right. So looking from left to right, I have this logarithm plus another logarithm. I can rewrite that using my product property. I would have 54 times 10, which is 540 inside of that logarithm. So again, what I did there is I multiplied the two arguments inside. So I had a 54 and a 10. When I multiply them, I get 540. Now I get to use the division property and get log base 3 of 540 over 20. Now we have written this as a single logarithm, but we can simplify this. 540 divided by 20 is equal to 27. So this is log base 3 of 27. Now, is that something I can actually evaluate? It is. 3 to what power will give me 27? That's what this is saying. So I'm just going to put in parentheses for us here. 3 to what power is 27? Well, 3 to the third gets me 27. So log base 3 of 27 is just 3. So this expression that we had at the beginning was just a complicated way of writing 3. Let's do another one like that. I have 1/3 natural log of t plus natural log of t squared minus 9 minus natural log of t minus 3. The first thing I'm going to do is take this 1/3 and bring it up as a power. So I get natural log of t to the 1/3 plus natural log of t squared minus 9 minus natural log of t minus 3. Now going from left to right, my first two logarithms I come across have a plus in between, so I get to multiply their inputs. Natural log of t to the 1/3 times t squared minus 9. And then I have a minus natural log of t minus 3. So now between my two logarithms, I have subtraction. That means I can use that division property. So I can write this as the natural log of t to the 1/3 times t squared minus 9 divided by t minus 3. And technically that's written as one logarithm, but we can simplify this. How? T squared minus 9 can factor. So I know that t squared minus 9 is the same thing as a t minus 3 times a t plus 3. So now you can see that t minus 3 can cancel that with the denominator. So my simplest answer is natural log of t to the 1/3 times t plus 3. So that was some practice taking an expanded logarithm and writing it back down as one single logarithm. This skill comes in handy when you have to solve equations using logarithms. All right, to finish up this video, I have one more example similar to this. We have a formula to learn, and then an example using that formula, and then we're done. So one more example before our formula. It's kind of a weird example. We have, given that log base b of 2 is approximately 0.356, and log base b of 3 is approximately 0.565, approximate log base b of 24. So notice we don't even know what b is in this problem, so I can't try to figure it out using that base. The only thing I know is log base b of 2 and log base b of 3. So my goal is to take this log base b of 24 and write it as combinations of log base b of 2 and 3. How do we do that? Well, let's think about things that multiply to 24. The first things I think of are 4 and 6. So I have log base b of 4 times 6. Well, that doesn't help us that much because that's not a 2 or a 3. But what are things that multiply to 4? Well, 2 and 2. And how about things that multiply to 6? 2 and 3. So now I have 24 written as just 2's and 3's. I'm going to rewrite it a little bit. I have log base b of 2 to the 3rd power times 3. Now using that product property of logarithms, this is log base b of 2 to the 3rd plus log base b of 3. And now I can use that power property to bring this 3 in front. And so now I get that my original log base b of 24 is the same thing as 3 times log base b of 2 plus log base b of 3. And now we're in good shape because our problem gave us log base b of 2 and log base b of 3. So I can plug that information in to get 3 times 0.356 plus 0.565. And when I multiply these two and add this stuff together, I get 1.633 as my approximation of log base b of 24. So now to finish this video up, we need to learn something called the change of base formula, and then do an example using it. So the change of base formula says that if we let a and b not equal to 1 be positive real numbers, then log base b of x is equal to log base a of x divided by log base a of b. So this formula allows you to change a logarithm of any base to logarithms of any other base. In particular, this allows you to change a logarithm of any base into a common log or a natural log. And you're going to get the same result regardless of which one you use. Now, why would I want to change it to a common log or a natural log? Because those are the ones you have buttons on your calculator for. So we'll be able to calculate all sorts of crazy logarithms by changing them to common logs or natural logs, and then we can use our calculator. Let's do an example. So first, we're going to estimate log base 6 of 23 between two consecutive integers. So remember that logarithms are talking about powers. So I have to think of powers of 6. And I want to find powers of 6 that are surrounding this 23. Well, 6 to the first power is 6. And 6 to the second power is 36. So I know that 6 is less than 23, which is less than 36. And I've written it with the exponents to emphasize the fact that this means that 1 is less than the logarithm base 6 of 23, which is less than 2. Those are just the powers on 6 that will get us that result. So here I have estimated my logarithm base 6 of 23 as being something between 1 and 2, even though I don't know what it is. I just know it's between 1 and 2. Now I'm going to use the change of base formula to show exactly what this is. So part B, use change of base with common logs to find log base 6 of 23 to 4 decimal places. So my change of base formula tells me that log base 6 of 23 will be equal to my common log of 23 divided by my common log of 6. And that is something that you can type into your calculator. Log of 23 divided by log of 6, and you should get to 4 decimal places, 1.7500. And now what's pretty cool is for part C, we're going to do the same exact thing, except we're not going to use the common log. We're going to use the change of base formula with natural logs to find log base 6 of 23 to 4 decimal places. So my change of base formula using natural logs tells me that log base 6 of 23 is equal to natural log of 23 divided by natural log of 6. And now, even though the natural log of 23 is very different from common log of 23, and natural log of 6 is very different from common log of 6, when you write it in this way with a ratio, you're still going to get the exact same result, 1.7500. So when you're using the change of base formula, it does not matter if you change to common logs or to natural logs, you're still going to get the same result. This log base 6 of 23 is always exactly equal to log of any other base of 23 divided by log of any other base of 6. So it doesn't matter which one you use, you're still going to get the same result. I personally like natural logs better because you use them more in calculus, and also, quite frankly, because you're writing one less letter, so it's a little quicker to write it. And I know that sounds incredibly lazy, but it's the truth. I like writing less letters. So you can use whichever one you prefer personally. That's all I have for you today. I hope this helped a little bit with logarithms and helped make them a little bit less terrifying. If you have any questions, feel free to drop them below, or you may come to office hours or email if you're one of my current students, and I will see you next time.